Okay, so yesterday I was finishing my lecture by introducing the Teichmüller space of genus G compact Riemann surfaces, marked compact Riemann surfaces, and we defined the function which are the length functions on the Teichmüller spaces that permits to define the topology, which is the topology for defined by this function. And so, in fact, I think I'm going to go quite quickly on these questions because part of this material was already described by different people this week. So I would like to say that so we get a topological space which in fact we can prove that it is homeomorphic to a ball of dimension 6g minus 6. So this is done by what is called the Fenchel-Ninsel coordinates on the Teichmüller space. And so we get, so let me just write a few things that are not at all trivial, but just I think I'm going to admit that. So we define the TG. So this is, I call the set of marked compact Riemann surfaces of genus G. So using uniformization theorem, we define the length functions, which define a topology on these sets. And using the Fenchel-Ninsel coordinates, we can see that TG is in fact homeomorphic to a ball of dimension 6g minus 6. And also what we have, and we did not discuss that yesterday, but I think it's quite clear, we have an action of the modular group on the Teichmüller space. So recall that here a marked surface is a compact Riemann surface of genus G plus a marking, and a marking M is a homotopy class of homeo phi from the reference surface, which is an oriented closed compact surface which is fixed once for all, to the Riemann surface X, right? And and so we have the modular group I'm going to take the positive one, which is the set of the group of homotopy classes of homeo of SG preserving the orientation. It is a group where the group law is given by the composition. Okay, if you compose diffeomorphism that I mean the composition preserves a homotopy class, so we get a group. This is called the modular group. I think of the surface SG. And this modular group acts on the markings by precomposition. Right? So we have an action of the modular group. So if you take a class psi in the modular group of SG, and you take a marked Riemann surface, so it is an equivalence class of marked Riemann surface, you can define the action of psi on this marked Riemann surface by just, this is a class of X, and you precompose the marking by, so you take an inverse of psi so that you really get an action, not an anti-action. So this defines an action of the modular group on the Teichmüller space. And in fact, we have a very nice thing, which is that the action of this group, considered as a discontinuous group, is proper on the Teichmüller space. So there is a theorem which says that properly discontinuously on Tg. And so the quotient of Tg by this group, equipped with the quotient topology, is a separated locally compact space, which is a orbifold. Okay, the quotient equals moduli space. Take the quotient by is a so of the same dimension. And in fact, this orbifold is not compact. As we remarked yesterday, we observed that in some families of curves, you have some degeneracies to singular ones. And these degeneracies describe the cusps, in a sense. So these families of curves in the moduli space go to the cusps, go to infinity in moduli space. Okay, so MG typically is not compact. Properly you consider the group, the modular group, with this discrete topology, yes. Right? This is the meaning of discontinuous. So it is proper in the sense that this means that for every P in Tg, there exists a neighborhood of P called U, such that if you take gamma in the modular group, gamma U is going to send U to something which intersects U only for a finite number of elements. This is the same as saying that if you look at the map from mod SG times TG to TG, this is a proper map. Sorry? This is a definition. Okay. Anyway, so just I don't want to go into that because I will spend all the lectures, and I think most of you know that, and it was kind of partially described in this week. So just to have an idea, if G is equal to 1, which is not good to take because it's not hyperbolic surfaces, but still, just to have an idea, this Mg is two-dimensional, and this is it looks something like that for those who who know, I just say that. So it's called the modular surface. It's edge, which is the Teichmüller space for G is equal to 1. Mod PSL2Z, in fact SL2Z, is the modular group in this case, acting on the upper half plane. So this is we get the modular curve in that case. G is equal to 1, and we see that it's not compact, right?
How to describe the boundary of the module space of
Sorry?
How to describe the boundary because it's uncompact?
Okay, so it can be compactified. I will not go into that, but there is a compactification. So there are plenty of compactifications. But basically, you add some singular curves, so curves with nodes. And there are different ones with different various interests. So it's a very complicated subject, but you can do that. There are plenty of compactifications. Okay. So now what I would like to do is to describe the analytic structure on that space. So this is really the matter of these lectures. So how do we do that? So it's kind of hard to do that. So the idea, I mean, the basic idea that we want to develop is that we want to build a complex structure on TG or on MG. This is kind of equivalent. So a complex structure which is invariant by the action of the modular group. And which has the property that if you take a family of curves, holomorphic families of curves with the definition of yesterday, it will define a movement in, so it will define a subvariety in Teichmüller space, which is holomorphic, right? So namely, if you take a family of curves as yesterday, so you have your space X, which is fibered by a map pi to a base B. So of course you can look at the map. So if you take a point B, you can fix a marking on a fiber, and then you can follow the marking by deforming the point B in the base. So you define like this a local map from B to Teichmüller space, and you want that this map is holomorphic, right? So I'm sure you can do that following the idea of Kodaira, but I am going to follow another road, which is which uses an analytic tool, a very powerful analytic tool, which is quasi-conformal maps. And we will see that the use of quasi-conformal map is extremely useful in this theory. So let me just recall what a quasi-conformal map is. Okay, so you take a map phi, phi from X, a Riemann surface, and between Riemann surfaces X and Y. And if phi is a, in fact, if phi is a diffeomorphism, it's going to be, at least it's going to be always a homeomorphism, but just assume for a moment that it is, so it is going to be a homomorphism preserving orientation. If phi is a diffeomorphism, so you can look at a, at a circle in Y in a tangent space to 1, to y. The circles are well defined because we have a Riemann surface, so we have a class of conformal matrix or emission matrix on the Riemann surface y. So the circles in the tangent spaces to y are well defined. And if we take the pullback of the circle by phi in x, we see that the circle has been distorted to an ellipse. And in fact, we can have a measure of how this is distorted, which is called the conformal distortion, which is the ratio of the small axe of the ellipse by the large axe of the ellipse. Right? This is a conformal distortion. So this is a radius R1, so R minus R plus. And there is a formula which is kind of easy to establish, which is that this conformal distortion is equal to to the norm of the quotient of the d bar of phi, which is the anti-holomorphic part of the differential of phi, by the d of phi, which is the holomorphic part of the differential of phi. Namely, you write the differential of phi, you decompose it as a holomorphic part plus anti-holomorphic part, right? And we know that if phi preserves orientation, meaning that the differential of phi is a orientation-preserving linear map, that is equivalent to the fact that the holomorphic part has a norm which is larger, strictly larger than the anti-holomorphic part. So this ratio is going to be less than 1. So right in local coordinates, it's just given by, so in local coordinates, of course, it's just given by d bar phi, the field dz bar times dz bar, right? Where these operators are the classical operators of complex analysis, right? So you see that this quantity is locally given by a function, which is a quotient of these two derivatives, times dz bar over dz. So it is what is called a Beltrami coefficient. And in fact, you can see that the norm of a Beltrami coefficient is well defined. So the modulus of the function appearing there is independent of the local coordinates chosen. And in fact, a proof is just remarking that you have this equality here. I mean, the norm of this Beltrami coefficient is just the quotient of the of the small axe by the large axe of the ellipse, right? So let me just so we will say that a diffeomorphism is quasi-conformal if this ratio is bounded by a constant strictly less than 1 over the whole surface X, right? And if K is a bound, if bk is a bound, we say that the diffeomorphism is K quasi-conformal. Now, there is a notion. In fact, the thing is that this is extremely interesting to consider this diffeomorphism, but the bad point is that if you look at the set of all these diffeomorphism, you know, you have something which is really nice if you really deal with holomorphic maps, is that you have compactness theorem. Namely, if you take a uniform limit of your holomorphic map, we know it is holomorphic. This is no more true if you consider K quasi-conformal maps. So you can get some sequence of K quasi-conformal diffeomorphism which tends to something which is no more a diffeomorphism. But still, you get something which is interesting in the limit, which is the notion of K quasi-conformal homomorphism. What is the definition? A K, so a homomorphism phi is K quasi-conformal if the following happens. So if you take a quadrilateral, what is quadrilateral is something in, so it is a Jordan domain with 4 points on the boundary of the Jordan domain in X. So you take Q X, a quadrilateral in X. So this is so, and the points we know, let's order them in the cyclic ordering. So when you have a quadrilateral like this, we know by uniformization theory of uniformization theorem that there exists a unique up to affine map, unique rectangle, which is bielomorphic to that quadrilateral. Namely, you have a bielomorphism from a rectangle so that the 4 points, so for 4 vertices of the rectangle are mapped to the 4 points on your quadrilateral. So you have a unique rectangle like that up to affine maps. So if you, for instance, you say that vertical edge is equal to 1, the length of the vertical and this one is a, so you can fix the rectangle in this way. So now you can look at the image of your quadrilateral by the map phi. So you get another quadrilateral like this, for instance. So you get a QY, which is in Y. And this one, you can also uniformize this by a rectangle. But this rectangle might be really different. So no. So it is, so a priori, if you don't fix anything, the rectangle is unique up to a affine map. So of course, if you take an affine map, I mean, a complex affine map, right? And if you fix vertical edge to be 1, then A is unique, right? Yes, you have to, yes. Right, you're right. You have to fix, right, it is unique if you want that this vertex is mapped to the, I mean, you say you label the vertex of a rectangle in this way. So the 1 is the 1 on the bottom and the left, etc. And in cyclic order. So the image of this rectangle is also a rectangle. So QY is also a rectangle. It is also uniformized in a unique way. So here we have phi of 1, phi of 2, phi of 3, phi of 4. And we have here an A prime, right? So the A prime might have changed, right, of course. So if phi is holomorphic, we have the same. But if phi is any map, it will have changed. And so we say that phi is quasi-conformal if and only if the quotient of these two quantities from above and by 1 over from below for any quadrilateral, right? So this is the definition of this is a geometric definition of a K quasi-conformal map, right? And in fact, I think you did that at least partially, but if you take a K quasi-conformal diffeomorphism, it satisfies this property. This is Grudge theorem. Grudge theorem. If you take a K quasi-conformal diffeomorphism from a rectangle, this rectangle A to this rectangle A prime, then A prime over A satisfies these inequalities. This is Grudge theorem. So it is a natural generalization, and in fact, it is the natural generalization. And so here, so of course, I'm really admitting everything now. I'm just describing the theory of quasi-conformal map in 15 minutes, so it's kind of, for those that want to understand and read a very nice book, there is a book by Alfors, which is called Quasi-Conformal Mappings. And this is kind of just.
Because if K equals 1, it gives A prime equals A.
Right? So it gives. Yeah, so you are completely right. Thank you very much for this remark. So, okay. So here, so let us say, okay, so you're right. Sorry. Can I just? Yes, so here, let us define this K is equal to the sup of. This is something which, for a quasi-conformal diffeomorphism, by definition, you assume, so this is a sup over X. Assume it is strictly less than 1. And this K is a big K, right? And so Grudge theorem says that it will be a little k quasi-conformal diffeomorphism in this sense will satisfy this for big K is equal to K, little k plus 1. Sorry. Yeah, it should be something like 1 plus K over 1 minus K, I suppose. Let me just think a little bit. Right. So for this value of big K, it will satisfy this statement. Thank you very much for this remark. Yeah, okay, you have this. So there is this book by Alfors. I was saying it is a very nice book. Alfors writes really well. So for those that do not know this theory and want to know, I mean, read that book. It's really nice. So let me just now give some analytical properties of quasi-conformal maps that we are going to use and that are extremely, so there are plenty of them. I just want to focus on two properties. So the first one I would like to mention is the fact that a quasi-conformal homeomorphism is differentiable almost everywhere, and its derivative is locally in L2. And reciprocally, if you have a homeomorphism having this property, and also you assume that so if it has a derivative defined almost everywhere, you can consider these quotients. So if these quotients are bounded on a set of total measure by a certain constant strictly less than 1, then in fact it is a quasi-conformal mapping in this sense. Quasi-conformal homeomorphism in this sense. So let me just say that phi, a homeomorphism preserving orientation, a preserving orientation is K quasi-conformal if and only if phi is differentiable almost everywhere with derivative in L2 lock and and we have this inequality almost everywhere, where little k and big K are related by this, this formula here. Okay? So this is a very nice analytical characterization of quasi-conformal holomorphism. It's very deep theorem. Okay, this is really deep, but and also, in fact, right. And here is another very deep theorem, which is due, in fact, I mean, it has a really long history. I mean, the finite point is due to Mordell. But it is a very deep generalization of a theorem which was known back to Gauss, in fact, which says that if you have any conformal structure on a surface, I mean, any holomorphic structure on a surface, so sorry, any almost complex structure on a surface is in fact integrable, right? So if you take any almost complex structure on a surface, which means that you take on every tangent space, you have an operator J whose squares is minus the identity, right? This is the definition of almost complex structure. Then, in fact, this almost complex structure integrates as a genuine complex structure. So you have holomorphic coordinates. So you have holomorphic coordinates to the complex number, mapping this almost complex structure to the canonical, I mean, usual complex structure on the complex number, where the operator is just multiplication by imaginary number I on any tangent space. And in fact, there is so in fact, Gauss proved this theorem for real analytic, almost complex structure. So he formulates the theorem differently, but anyway. And the regularity of the almost complex structure was lowered in history. And the last step of the theorem, which is the following. So suppose. So let me just make a definition before. So I'm going to state Morris theorem here and now, just before I just make a definition. So let me just define what is the Beltrami coefficient. So the Beltrami coefficient, so we just say that just before as an example, but a Beltrami coefficient on a Riemann surface X is an object, say, I don't know if it is a tensor or something, which takes the form a function of z times dz bar over dz in any coordinates. And if you change the coordinates, so if such that, if W so is another coordinate, so this object, the new form of this object is going to be, so you can express as a function of W, and you will get, so here you will get the derivative of this function z of w appearing there times dw bar over dw, right? So you get a new function in the w coordinate, which is this function so of course so the new I'm saying that the new function in the w coordinate transform according to this rule here. So f is a map with real values. So f, so where, so it will be important. In fact, we are going to consider Beltrami coefficient with measurable maps. So measurable Beltrami coefficient. So here, it depends. So a priori, f is going to be a map with complex values and with certain regularities that you can, I mean, you can specify, you can consider several types of Beltrami coefficients. So this map is not at all holomorphic, right? Anyway, it would have no sense because you see that you have, you multiply this, if you change the coordinates, you multiply the function by something which is not holomorphic. You have no chance to define a good concept if you take f holomorphic. So f is a map which is differentiable, so analytic, C1, continuous, or measurable even. And we are going to consider measurable maps, in fact. So here, so typically, f is going to be measurable, so defined almost everywhere with respect to the Lebesgue measure, and bounded in infinity norm. So in fact, we are going to assume that the infinity norm of f is bounded by a constant which is less than 1 in general. So in general, this will be the kind of Beltrami coefficient we are going to consider. So of course, for quasi-conformal diffeomorphism, this is exactly what we get by the discussion that we had before, right? I just tell you that if you consider a K quasi-conformal homeomorphism, by this analytic characterization, we get a Beltrami coefficient which is measurable with this condition. So here we get that the infinite norm of f is less than little k, right? And so we can, so of course, just I want to say that. So in fact, so don't think about the regularity in what I am going to say now, but if you want to define a complex structure on a Riemann surface, so a null structure on a Riemann surface, in fact, if you think a little bit, you will see that this is exactly equivalent to defining a Beltrami coefficient. Because in fact, what you want to, so I say that almost, is the same as Beltrami coefficients bounded by 1, strictly bounded by 1. At any point. Why is this so? Because if you think, so either you can think of a complex structure, so suppose, so you have a tangent space to a point x, right, which is identified with a complex number because we have already a complex structure on x. Now we want to define another one. So say I'm calling z the coordinates here in the complex numbers. You can think of a complex structure as being an operator whose square is minus the identity, but you can also just say that this is an identification of the tangent space of x with a complex number in another way, which preserves orientation, right? So this is a R linear map from the tangent space of x to the complex number, but which is not this one, another identification, right?
Why is it clear that when you change coordinates, you keep the probability of being smaller than 1?
You see here that when you change coordinates, you multiply by the derivative of z with respect to w, where you take the conjugate, and then you divide by the derivative. So the modulus of this is 1, right? So in fact, the norm of a Beltrami coefficient is well defined at any point, right? So the norm of dz is the same as the norm of dz bar, right? This is conjugate complex numbers. So, okay, so I was saying that a complex structure, you can think of that as being better an identification of tangent space of X with a complex number, which is R-linear, but which is not R-linear in another way. So which is not C-linear, I say. And this identification is well defined up. Okay, so and this identification with a complex number should be well defined up to multiplication by a complex number, right? Up to C-linear automorphism, post-composition by C-linear automorphism, right? So if you take a R-linear map from C to C, so you know that every R-linear map can be written as dz plus mu times dz bar, where mu is a certain complex number. I mean, a priori, any R-linear map can be decomposed in this form with alpha, beta complex numbers. But if you allow to post-compose by a C-linear map, so this is going to be alpha times dz plus mu dz bar, where mu is a quotient of beta by alpha. And so you can assume that your C-linear map, your R-linear map is given by this formula, right? And in fact, the quotient of this antilinear part of the R-linear map by the C-linear part of the R-linear map is well defined, and it is a Beltrami coefficient. Okay, so this gives you this dictionary between the most complex structures on X and Beltrami coefficients, right? So you really have to think that. Okay, so now. Is there any questions till there? I mean, so now there is a theorem which is very important. I'm going to state, which says that if you take a measurable, almost complex structure on the Riemann sphere, then in fact it is so first, it is integrable, and moreover, it is biholomorphic to the Riemann sphere itself. So let me just state the theorem.
Why the coefficient on the last black body is smaller than 1?
Because you assume that the map preserves orientation. So if you take dz plus mu dz bar, where mu is a complex number, so make this exercise, you will see that the map preserves orientation if mu is a complex number of modulus less than 1, strictly less than 1. If mu is of modulus 1, it is not bijective, it has a kernel, this map. And if mu has modulus larger than 1, it anti-preserves orientation. This is an exercise, you will see, it's kind of easy. Yes.
Things are applied or used right till now.
No. Now I was saying that I am following another road. I mean, of course we will get to that at the end, but we just described analytic structure on Teichmüller space in another way. Okay, so let me just state the theorem of Mordell and. So Mordell's theorem is the following. So you take any Beltrami coefficient on the Riemann sphere. So, yeah. which is measurable with and bounded almost everywhere by a constant strictly less than 1, then there exists a K, so unique K quasi-conformal holomorphism phi mu so that its conformal dilatation, which is defined almost everywhere, is equal to the Beltrami coefficient we started with, such that first, this is the most important equation. And if we want a unicity statement, we need to. So this phi mu is going to map the almost complex structure defined by mu to the standard structure on the Riemann sphere. Right. So this phi mu maps. So you have two CP1. So you have a CP1 here with a kind of different complex structure. So I'm drawing a kind of fields of ellipses here, given by the Beltrami coefficient mu of z. So these fields of ellipses is just defined by, say, the set, the ellipses defined by 1 plus mu is equal to 1 in the tangent space to x, say. And so these fields of ellipses is going to be mapped by phi mu to the field of round circles. This is the idea that you have to have in mind. This is the meaning of this equation. It's the geometric meaning of this equation. This is the first point, and the second point is that phi mu fixes 0, 1, and infinity. Of course, this second condition is to have a unicity statement, and we can, of course, we have unicity in general, because if you have a solution to that geometric problem, so sending these ellipses to circles, of course, you can post-compose your solution by a map that maps the fields of circle to the fields of circles, namely a holomorphic map of P1 to P1. And we know that there are plenty of them. So we have an automorphism group of CP1, which is PSL to C, the group of Möbius transformations, which acts freely transitively on the set of triples of points, of distinct points in CP1. Okay? So we can fix the position of phi mu on 3 points. So this is the meaning of this condition, and if we do that, we have unicity. Okay? Moreover, so this is a very impressive theorem, but moreover, we have a very nice thing, which is that phi mu, I mean the map mu to phi mu is holomorphic. So what is the meaning of that? In fact, this is something interesting, which is related to the notion of, yes?
So is the Beltrami coefficient also almost everywhere differentiable, continuous at least?
No. The Beltrami coefficient is only. So I say that you have, if you take K quasi-conformal homomorphism with this geometric definition I gave, in fact, it is differentiable almost everywhere. You cannot have much more than that. And now the problem is the inverse. You start with, say, the conformal distortion of a quasi-conformal homomorphism, which a priori is just measurable. And in fact, you can recover the quasi-conformal homomorphism by this. So this is really something which is very well, I mean, the theory goes in both directions. Yeah. Quasi-conformal map gives you differentials, which give you Beltramic coefficients by the conformal distortions, and you can come back to that.
In this norm, infinity, you really mean the infinite norm of just the function mu of z?
Yes, this is exactly the same thing. So the norm of that is 1. Okay? Yeah, you can just forget about that. But I will write the norm of a Beltrami coefficient. I mean, this is the norm of the function. It's the same thing.
This is for the CV2, the CV1, but the measurable Riemann mapping theorem is for just only for the disk. Measurable Riemann mapping theorem.
Well, you can measure. What do you mean by measurable Riemann mapping theorem?
Just a version of on D.
Yes, you will certainly have a version of that on the disk D. We will see that. So you can just put a Beltrami coefficient on the unit disk. You put 0 outside the disk. It's measurable, and you apply that, and you get that your fields of, your most complex structure on the unit disk is mapped, to the standard one by your solution, and then you can apply Riemann uniformization theorem to the image of your domain to get exactly the map you get.
That version is due to Albert's Bers. This one.
No, this is not. This is Morel's theorem. This one. This is not Alford's Best. So Alford's Best, they used that fact.
Can you say again, what is the meaning of the 1 plus mu?
Okay, if you look at this equation, what it gives, it's 1 plus. Yes, I was kind of. So it means that if you rewrite that, it is I hope I have not made a mistake, another one. Yeah. I have to multiply by dz, right? I mean, what I want to say, yeah. Let me just think. Yeah, you want, so this is, okay, you want, no, this is, the equation is that one you want. So yes, so, sorry, I'm sorry. This is not, the ellipses are given by this equation. Okay, this is the map from the tangent space at Z to the complex numbers that gives you the new complex structure induced by mu, right? This is our linear map that gives you a new complex structure. So the circle for this new complex structure are given by this equation. So the modulus of that is equal to 1. But in the original complex structure, there are ellipses, right? I'm sorry, yes, I was thinking I made another mistake here. So these ellipses are given by this equation, sorry. So what is the meaning of that? So in fact, if you take the set of, say, homomorphism from a Riemann surface to itself, in fact, this is a group, but it has, in a sense, a complex structure, infinite dimensional complex structure, which is the following. You can say that a homomorphism varies holomorphically if you fix any point. So you have, suppose you have, so it means that, so this is that for any z, you fix a point in CP1, the map mu maps to phi mu of z is holomorphic. So if you have a family of homomorphism depending on the complex parameter, you say it is holomorphic if for every point, if you fix a point, you look at the image of your point by your homomorphism that varies with the parameter. This is a complex, this is holomorphic map. Yes?
Beltrami coefficients times P1 to the Beltrami coefficients, the space of Beltrami coefficients times P1, putting phi mu at each. And you would require that it's holomorphic. So this would be another definition.
So you mean mu?
You take the map mu z goes to mu phi mu z. And you view this as a map from the space of Beltrami coefficients times P1.
Isn't it the same?
It seems to be weaker because it seems to be one variable intersection. I don't know whether it's weaker or not weaker.
I would say it's the same, but
it looks like it's the same. But there's an holomorphy in another direction.
okay. So
we are doing a Banach analytic stuff because of mu.
no, I see what you mean.
I don't know.
No, I see. I see. I have to think. About that.
Okay. We don't know.
Yeah, I don't know. I don't know. At least I don't know. But, okay. So let me just now. So we have. So I cannot make a pause. It doesn't make sense now because I have 30 minutes left. So I'm going to finish. So these 30 minutes, I'm now. So those are the two main analytic tools I am going to use, and I admit. So the proofs, I mean, deserves. It's really deep theorems, and so we just are going to use these theorems, right? So now. So what I would like to know now, to do now is to define the analytic holomorphic structure on Teichmüller space. Right? So as I promised, on G. So what I am going to do is to define the holomorphic structure on Teichmüller space. I'm going to pick an element in the Teichmüller space and to define the holomorphic structure using that element. Okay, so I am going to define a holomorphic structure. And then, this is nice, but we will get a family of holomorphic structure on Teichmüller space, and we want to see that they are all the same. So to get something which is invariant by the modular group, for instance. And to get something which, I mean, which is intrinsically defined, canonically defined, right? So, so let us pick an element and now if we do that, if we take any other element in Teichmüller space, we can take a quasi-conformal homomorphism, even diffeomorphism if you want, from X to this new element preserving the marking. And we can pull back the complex structure on this new element of Teichmüller space to our complex Riemann surface X, and we will see this complex structure as a Beltrami coefficient, right? And now, so Teichmüller space viewed in this way is going to be the set of Beltrami coefficients, but there is an equivalence relation. Some Beltrami coefficients, of course, are the same. For instance, you can, so if you take X, an element Y, so for any Y, so let me just do the conventions I was doing yesterday. So pick AK, quasi-conformal, Romeo, say psi from X to Y in the marking. So in MY, so preserving the marking, say, and associate to this quasi-conformal map its Beltrami coefficient. B of psi is, by definition, it's the Beltrami coefficient of psi, so this is a Beltrami coefficient which is measurable and whose norm is infinity's norm is strictly less than 1, right? But of course, you can consider another one, another quasi-conformal homomorphism, and you will get another Beltrami coefficient. So it is not the set of Beltrami coefficients that we have to identify to Teichmüller space, but an equivalence, so equivalence class of Beltrami coefficients, which is defined like this. So you will get that Teichmüller space is a set of Beltrami coefficient mod 2 are equivalent if there exists a K quasi-conformal homomorphism from X to X, sending the first to the second one, right? So let's say this way. So so by this procedure, we get that we get a description of Teichmüller space, which is T of G is naturally, say, in bijection with a set of measurable Beltrami coefficients on X with infinity norm strictly less than 1. So in a geometric way, it's a kind of fields of ellipses whose eccentricity is bounded uniformly in X. Mod a relation, and the relation is mu, a Beltrami coefficient on X is equivalent to mu prime, another Beltrami coefficient on X. So call this a set of Beltrami coefficient, measurable Beltrami coefficient on X bounded by 1, B1 of X. B for Beltrami and 1 because it's bounded by 1. Okay? So if you take mu and mu prime 2 Beltrami coefficients in B1 of X, so they are equivalent if and only if there exists a quasi-conformal Romeo phi from, so it's better to write this. Yeah, let's write phi, it's not equivalent, but from X to X, right? Such that if you pull back the Beltrami coefficient mu prime, you get mu, and phi is homotopic to the identity. Right? And now I will not go into a lot of detail. I just want to explain why we get a complex structure from that. And then you have to do two small exercises which are really easy to do. I mean, K quasi-conformal homeo means there exists K. There exists a little K strictly less than 1 such that blah, blah, blah. Such that the map is K quasi-conformal. Right. And here I can also, right? I mean, the dependence on K, you don't fix a K, right? In this theory, you just know by quasi-conformal homomorphism, you just know there exists a K. Okay, in general. Okay, so now here we have a unit ball in the Banach space, which is a Banach space of L infinity. So you take the measurable Beltrami coefficient and you take the norm, the unit ball with respect to the infinity norm, right? So it has a complex structure. It is a C-linear Banach space. It has a complex structure, right? And so now we take this unit ball, and now we want to take the quotient of this unit ball by the action of a group. But as I said, there is a notion of, so this group is infinite dimensional. The group of all quasi-conformal homomorphism of the surface, which is isotopic to the identity. But it has a kind of complex structure. We can say what is the meaning of holomorphic family of homomorphism, as we just said before. And my claim, and this is really easy exercise, is that the orbits of this group action are holomorphic. I mean, the action is holomorphic. The action of the group of quasi-conformal homomorphism on the set of Beltrami coefficients is holomorphic with respect to these structures. And this is kind of really easy computation. So this is the first computation that you have to make. And if you believe that, so this has, I mean, of course, we will get a complex structure on the quotient. And this is the complex structure we are going to define. I mean that the action is holomorphic. I mean
the action of each element is
right.
holomorphic.
Right. And also, I mean, this is not that each element acts holomorphically. I mean that so if you take, for instance, if you take so you take a family of maps which depends holomorphically on a parameter z, right? And you take also a family of Beltrami differential which depends on another complex parameter holomorphically. Then you apply the homomorphism at that parameter to the Beltrami coefficient at that parameter, and you get holomorphic map also. And so this is the first thing, which is a local computation. And the second thing is that now you will get a complex structure associated to a certain Riemann fixed point on the Teichmüller space. So you can move this point. But of course, you have an identity. So if you change the x, you will get a priori another complex structure. But I say the complex structure is not going to change. And this is another exercise to do. So if you have a Beltrami coefficient, so if you take two Riemann surfaces, you take a quasi-conformal map between these two Riemann surfaces, any complex Beltrami coefficient on the second one, you can pull back to a Beltrami coefficient on the first one, and this map is holomorphic. I claim that. And I claim that this map is going to give you an holomorphic identification between the two complex structures on your Teichmüller spaces. Right. So I will not go into this detail. I mean, in fact, this is, it is complicated to do. I mean, just do formally the computation, you will see that it works. So then you have plenty of issues concerning the fact that we are considering infinite dimensional spaces, etc. There are plenty of difficulties. I will not enter into those, but just formally you can see that it works. It's really easy to do that, and I really invite you to do these two exercises to see that it works well. And so just as a conclusion, just to know how we can use this complex structure is kind of, so how do we, for instance, to understand a complex structure, a very nice thing to do is to understand its holomorphic functions, so its sheaf of holomorphic function. So what is the sheaf of holomorphic function on Teichmüller space? Well, as I said, is the following one. So you take, so this is the sheaf of functions on this ball, okay, which are holomorphic. So here it's really easy to see because we have a Banach space. So it's a holomorphic function on that ball that are invariant by this relation. So this defines the sheaf of holomorphic function on Teichmüller space. And this is what we are going to use, in fact. Okay, okay, so I have 15 minutes left for this, to the end of this first lecture. So I don't want to say more about the complex structure on Teichmüller space. I think it's kind of enough here. But I would like to state a theorem that will be very important for the next lecture, which is a theorem of Bers, saying that Teichmüller space embeds holomorphically to a bounded domain in C 3G minus 3. So I don't know if my English is very good here. So what it means that there exists a holomorphic embedding of TG to C to the power 3G minus 3, whose image is a bounded set. It's an open set which is bounded. And in fact,
respect which the metric, because we have many metrics on Teichmüller space.
There is no metric statement here. This is holomorphically, so I'm not considering any metric on Teichmüller space here. Yeah, it is polynomially convex. So this is
Not linearly convex.
no, not at all. In fact, the image. So we don't know a lot about the image, but it seems to be a fractal thing. So it will not, at least, I mean, it will not be convex. I don't know if we have a proof, but pictures shows that it is not convex. However, it is polynomially convex. So you like this side. This is not a theorem by Bers, I think it's a theorem by Aaron Price, I think. But anyway, so we will prove this theorem, I mean, or at least describe how it works. Next lecture. So let me just finish this by introducing some material which are going to be very important for the proof of that theorem, and also, maybe I should, sorry. So I'm going to speak now about projective structures on surfaces. To give the definitions which are going to be useful for the next lecture. So I'm just kind of changing the topic now for this 10 minutes. So by projective, I mean CP1, a structure modeled by CP1 with a group of Möbius transformation acting on that. I mean a PSL2C CP1 structure here. So so I'm going to consider hyperbolic Riemann surface to begin with. Maybe let me just begin by some general definition, and then I will go to the hyperbolic Riemann surfaces. So the definition of a CP1 structure I'm going to take is the following. You have X, a Riemann surface. So a projective structure on X is an equivalent class of maps from the universal cover of X. So these maps are called developing maps to CP1. And what we ask is two things. So we ask that these maps should should be equivalent with respect to representation to the group of automorphism of P1 first, and that are so namely they satisfies d of gamma x equal, so x tilde say, rho of gamma d of x tilde for any gamma in the fundamental group and any point in the universal cover of X. And this map should be so holomorphic and local biholomorphism. So say holomorphic inertians. And the equivalent class that we are going to ask for this kind of maps is D is equivalent to D prime if and only if D prime is a composition of an automorphism of P1 with D. So in fact, these kind of structures appeared historically in the study of differential equations on Riemann surfaces. So if you take, say, first order linear equation on X, so suppose X is a domain in C, for instance, you take a holomorphic first order differential equation, or second order differential equation, say, better. And so you take a basis of solution of that differential equation, and you take the quotient of these solutions. This quotient is going to define a map D, which is a local diffeomorphism, holomorphic. It will satisfy an equivariance like that, where the representation is just given by the monodromy representation of the differential equation. And in fact, it is not well defined because you pick a choice of a basis of solutions of your differential equation, but you can make another choice and you will get that the new map differs by the first one exactly in this way. So in fact, it's really related to the theory of second order differential equation originally, and it's extremely useful concept that we will use. So this is the concept of a projective structure. In fact, normally we say a projective structure is an atlas of maps, charts from the Riemann surface to CP1 that differ by post-composing by a projective map. But those maps of your atlas, you can extend them analytically to get on the universal cover of X to get these developed maps. For those who were more confident with this definition with atlas, projective atlases.
You mean ME in PL2CIC?
Yes. The last line.
Yes. Thank you. Right. Now we can look at the moduli space of projective structure on a given Riemann surface. And there is a very nice thing, which is that this space can be well understood because of an operator, and this can be well understood. In fact, it is an affine space, an affine complex space, directed by the set of holomorphic quadratic differential on the surface X. And, the hint for that is a Schwarzial derivative. So I'm going to describe that in the case that X is hyperbolic. So I suppose X is the quotient of upper half plane by a Fuchsian group. So yesterday, I think I defined Fuchsian group by saying that those are discrete subgroup of automorphism of the unit disk. But of course, I am changing the model here. Take the model of the upper half plane. It will be more useful for what is going to happen this afternoon. Fine. And now you see that saying that we have already a complex projective structure on this X coming from the fact that the Fuchsian group acts by homographies on upper half plane. So we get the structure on X. And now, if we have another one, we can consider the following. So suppose we have D. We can consider the Schwarzian derivative of D. So the Schwarzian derivative, I'm going to denote it like this because I'm going to, so this is a certain differential operator, which is, you take, so I take a projective coordinate for the, say, uniformizing projective structure on X. So this is a Z coordinate in the upper half plane. And I take the second derivative of D over the first derivative of Z in this coordinate minus 3/2 times second derivative of D over first derivative of D squared. And I multiply this by dz squared because I say that all this business is related to holomorphic quadratic differentials, right? And in fact, so this is a differential operator, a priori kind of complicated, but it satisfies an extremely useful co-cycle relation, which is that if you have, say, you have some, I'm going to say something about local diffeomorphism from the complex number to the complex numbers. So you take local diffeomorphism from the complex number to, and you have, so suppose phi so our holomorphic diffeomorphisms, and U VW are open set in the complex number, or CP1, but let's say it's a complex number. So then you have the following co-cycle relation, So if you consider the composition, the Schwarzian derivative of the composition of these 2D homomorphisms, you get Schwarzian derivative of phi plus pullback of the Schwarzian derivative of psi. Right? Get this cosecant relation. And also, another extremely important property of the Schwarzian derivative is that it measures how far is your map D from being a projective map. So S of phi is equal to 0 identically if and only if phi is a projective map. Möbius map. So in fact, if you use these two properties, you can just, prove them by computations. Those are kind of hard. You can do that. But of course, there are some more clever way to prove these properties. But this is checkable. You just take your next 30 minutes and you do these computations. But if you have this computation in hand, you can prove that S of D does not depend on D, in fact. So if you take, for instance, you want to prove that, so D is not well defined. So there are several things that you want to prove. You want to prove, for instance, that S of M composed with D is the same as S of D. But you apply the cosecant relation, it gives you S of D plus D star S of M, but M is a projective map, so this one is 0, right? So that
S of M plus D plus M star of S of D.
no, this is. I think I'm right. So you take the Schwarzian derivative of the first map, and you take the pullback by the first map of the Schwarzian derivative. Okay. So in fact, it's really. So and the same for the invariance. If you want to prove that, so you want to. So if you have a projective structure on your X, you get a quadratic differential on the universal cover of X, but this quadratic differential, in fact, it is invariant by the group because of the equivalence condition. And this can be seen really easily. So if you take S of D composed with gamma, where gamma is an element of the fundamental group of X, so then you get S of gamma, which is 0, plus gamma star of, oh, sorry. Okay, no, sorry, I don't need to do that, so maybe, so this is S of O of gamma composed with D, right? And so this is S of D, so this is the same argument as before. So this is 0, and so you get invariance of this holomorphic quadratic differential by the group action. And so in fact, you get a map from the set P of X, which is a set of projective structures on X. So since it is a set of holomorphic maps on X, it has a it has a well-defined topology, so namely the compact open. And in fact, it has a holomorphic structure. You can say that what is the meaning of a holomorphic family of maps, etc., etc. You get a map from projective structure to holomorphic quadratic differentials on X. So for those who don't know this kind of notation, this is a set of holomorphic quadratic differentials this is a vector space, complex vector space. And this is given by the Schwarzian derivative, as we just explained. And this map is, in fact, an identification. So we just proved that. So in fact, we have to prove that if we know the Schwarzian of a map, we know the map up to post-composing by a Möbius transformation. And this is also true. Should have noted this property here. So subjectivity, you have to prove it. So of course, this is also, so if you have a quadratic differential, you can solve the Schwarzian equation, Schwarzian derivative of function equals this quadratic differential. I mean, this is, all this has to be proven. And so there are some works to do, but we have.
The claim is what? Bijection or biholomorphism? Or
This is a biholomorphism.
Left-hand side is not a vector space.
Okay, I will stop here, and we will use all these things this afternoon. Thank you.